Have you ever wished you had a crystal ball? Something that could just tell you what's coming next? Well, believe it or not, statisticians have basically been building their own version for years. Today, we're going to peek inside that toolbox and demystify one of the most powerful predictive tools out there, linear regression.
So, this gets us to the big question, right? Can statistics actually predict the future? Now, we're not talking about predicting lottery numbers. That's just random chaos. But what we can do is uncover hidden patterns in the world and use them to make some amazingly accurate forecasts. The key isn't magic, it's math.
And this is the perfect way to think about it. On one side, you've got your magic crystal ball. Looks cool, I guess, but it's totally unreliable. On the other side, you have a statistical model. It's not mystical, it's driven by cold, hard data. You don't have to believe in it, you can actually test it. It's not a decoration, it's a real predictive tool. And today, we're going to build one.
So our journey starts with trying to find a little bit of order in what looks like chaos. Just imagine a bunch of data points scattered all over a graph. Our first big goal is to find that one single perfect line that kind of cuts through all that data and shows us the trend.
It seems like a simple question, doesn't it? But think about it. If you have a scatter plot, how do you know exactly where that line should go? If you just eyeball it, the line you draw is going to be different from the line I draw. So how do we find the one line to rule them all? Well, of course, statistics has an official rule for that.
And here it is. It's called the Least Squares Criterion. Now, I know, it sounds super complicated, but the idea is actually pretty simple. See, for any line you draw, there are going to be gaps between your line and the real data points, right? We can think of those gaps as errors. The best line, the only right line, is the one that makes the grand total of all those errors as tiny as mathematically possible. So how do you actually find that perfect line? Well, it's a pretty straightforward process. First, you just draw a line, any line, through your data. Second, for every single data point, you measure that vertical gap, that error, between the point and your line. Third, you square all those little distances. This just makes sure all the numbers are positive. And finally, you add them all up. The winning line is the one unique line where that final number, that total sum, is the absolute smallest it can be.
Okay, so drawing a line on a graph is cool and all, but to really unlock its predictive power, we need to translate that picture into the universal language of math, a formula. This is really the secret recipe for our statistical crystal ball.
And here it is. I know, it might be giving you some high school algebra flashbacks, but stick with me. Because this simple little equation is the engine of our entire prediction model. It tells us everything we need to know. So let's break down what each of these little pieces actually means. First up, we've got y hat. Now that little hat on top of the y, it's actually super important in stats. It's the universal sign that we're talking about a prediction, or an estimate. See, real-world data is messy, right? The points almost never land perfectly on the line. So y hat is our model's best guess for where a point should be. Next up is b, the slope. This is kind of the action hero of the equation. It tells you how steep the line is and which direction it's going. Put simply, for every single step you take forward with x, the slope tells you exactly how far up or down you can expect y to go. It's the engine of change in our model. And finally, we have a, the y-intercept. So if the slope is the engine, you can think of the intercept as the anchor. It's our starting point. It tells you exactly where the line hits the vertical axis when your x value is 0. It basically locks our predictive line into place on the graph.
All right, enough with the theory. This is where it gets really fun. We're going to take our formula, we're going to plug in some real numbers from our source material, and we're going to make an actual prediction. Let's put this crystal ball to work.
Okay, so here's the specific equation that came from our source's data. They were looking at the link between a patient's diastolic blood pressure, that's our x, and the number of doctor's appointments they had. That's our y. This formula gives us a super precise prediction. For every single point your blood pressure goes up, the model predicts a 1.1 increase in doctor's appointments. And using it is just so simple. First, you start with your equation. Second, you take a new piece of info, like a new patient's blood pressure, and you just plug it in for x. And finally, you do the math, and boom, out pops your prediction, your y hat.
All right, let's give it a shot. Imagine a new patient walks in, and we measure their diastolic blood pressure at 80. Using our new formula, what's our best guess for how many appointments they might need this year?
And the answer is 8. We just plug it right in. 1.1 times 80 is 88. Then you subtract 80 and you get 8. And just like that, our statistical crystal ball gave us a specific, data-driven prediction. See? No magic, just a little bit of math. But wait a second. Making a prediction is one thing. Knowing if that prediction is any good, well, that's something else entirely. And this might just be the most important step of all. We have to grade our model to see if we can actually trust this crystal ball we just made. And this is so critical. Because here's the thing. You can feed any data into these formulas, even a totally random cloud of points that looks like a swarm of gnats, and it will always spit out a line for you. But a line based on randomness is completely useless. So how do we tell the difference between a powerful model and a worthless one?
We use this, the coefficient of determination, but everybody just calls it r². Honestly, you should just think of it as a report card for your model. It gives it a grade from 0 to 100%, and it tells you exactly what percentage of the changes in y can be explained by the changes in x.
And the best part is, calculating it could not be easier. You literally just take the correlation coefficient, r, and you multiply it by itself. That's it. A strong correlation, doesn't matter if it's positive or negative, will always give you a high r². So, for our example with blood pressure and doctor's visits, the correlation r was a very strong 0.95. When we square that number, we get about 0.90, or 90%. I mean, come on, that is an A+ on our model's report card.
And this donut chart shows you exactly what that 90% means. It's telling us that our one single variable, blood pressure, can account for a massive 90% of why the number of appointments goes up and down. Only that tiny 10% slice is left unexplained, caused by, a bunch of other random factors.
So the official way to state this conclusion is pretty powerful. 90% of the variation in the number of appointments is explained by the variation in diastolic blood pressure. This proves our crystal ball isn't just making wild guesses. It's based on a really strong, reliable relationship. We can actually trust its predictions.
And that brings us to the end. We've gone from a scattered mess of data, found the one perfect line to describe it, turned that line into a predictive formula, and then we even graded its performance. So I'll just leave you with this thought. From the hours you study and the grades you get, to the steps you take and your energy levels, what hidden relationships in your life are just waiting for a best fit line to reveal them?